In the last video, we took a look at motivating the fact that the impulse response of the specific system can be determined based on the transfer function. But what we saw is that once you started writing out that definition, essentially that convolution operation, as you chain together essentially some sort of input going through a block into producing an output, that relationship became more and more complex. And so what we'd like to demonstrate in this activity is by using the definition of the Laplace transform, essentially write out the definition of this Laplace transform, and our goal is to do some interesting calculus to get us down to the point where we can separate that into the Laplace transform of the impulse response and the Laplace transform of the input. And so that means that what this is ultimately saying, since this is what we're trying to prove down here, is the fact that the output can be written simply as a product of the Laplace transform of the input and the transfer function, which is a huge simplification from what we had written down for the convolution operation. So this is just going to require writing down the definition of Laplace transform of y, writing y as essentially the convolution that we talked about, and then simplifying that with the objective of getting that into this separation that we get here with the multiplication. So go ahead and pause the video and go ahead and attempt stepping through this process just to justify that we can now use this really handy identity when we do our block algebra. All right, so the first step in proving this is to just write out what the Laplace transform. So this is the definition of the Laplace transform. Just take that integral with this exponential term, and this is the output signal y. When we want to then describe the fact that y is the output of some transfer function block with an input coming in u, then we can write that based on the convolution operation that we discussed in the previous video. So now we're putting the essentially the delayed version or the shifted version of the impulse response with the input, and so now what you see is we've got these two integrals, and we also have different integrands. So we have integration variable tau and integration variable t. And so what we'd like to do is we'd like to separate these. And so this hinges on the fact that we're going to use the separability, the fact that it's easy to separate terms in the exponential, whereas here you've got this t and this tau in the same function, and that's difficult because we're proving this for any h. So what I'd like to do is go ahead and represent. We're going to let this quantity be a new variable, which we'll call sigma. And then what we'd like to do is now we're just going to write this in terms of tau and in terms of sigma. And what that does is it puts this sum now into the exponential, but that's easy to separate. And so we're going to just figure out what t is, because that's what we have to resubstitute in here. And we also have to substitute it in to figure out what dt is. So if you look at this definition, then we just rearrange this to get t is equal to sigma plus tau, and so that's what gets substituted in here for t. And then if we take the infinitesimal differentiation element, the dt, then this tau is considered a constant, and so just dt is equal to d sigma. So we just replace dt with d sigma. That's an easy replacement. And so now that we have this, now we can separate this exponential. The exponential rules for this is easy. It's e to the minus s sigma, and then e to the minus s tau. So when you have a sum like that, you can just split it into two different terms that are the product of each other. And so now that you have this, now this is all multiplied together, right? And so now the idea is that we're just going to shift this around, and it's actually the continuity. We assume that these things are continuous, so that's the nice math technicality that we have to assume in order to pull this guy outside of this this integral and pull it over here. And then similarly, where it's the continuity of this term e, this exponential, that allows us to essentially bring that piece into this inner integral with u. And now that we have these two different terms, now they're still all a product of each other, but now these are all in terms of sigma, and these are in terms of tau. So there's no integration that's happening across these two different integrals. But if you look at this, this is merely the definition of the Laplace transform, just using a slightly different variable. And this is the Laplace transform also using a slightly different variable than we've done before, tau and sigma. And so this is going to be the Laplace transform of u, and this is the Laplace transform of h. And so that's where we get these two different terms, and this product in between is simply because this is a product here. And so now we come back to the slide that we saw before, and we had these very nasty, increasingly nasty operations that happen in convolution when we're dealing with time domain signals. And when we change this into the Laplace transform domain, so these arrows represent we're taking the Laplace transform, now this operation becomes very easy. And so we can write Z1 as simply the product of its Laplace transform of u and the transfer function h1. And so that's what this is. Now, if we wanted to figure out what z2 is, that's simply just the product of z1, the Laplace transform of z1, and the transfer function h2. And so we just plug in what z1 is, and now we just get this expanded form. And similarly, if we wanted to find y, it would simply be the product of the input Laplace transform z2 and this transfer function h3, again substituting in for z2, that's this bit, then that gives us this entire result. And so now doing block diagram algebra makes this super easy to calculate the output, the Laplace transform of the output from the input based on just these chains of these multiplications that we'd see in terms of these transfer functions. And we're gonna continue to explore block diagram algebra. This is the kind of first fundamental piece, and when we get to feedback systems, we'll start to take a look at a variety of other different block diagram algebras that will help us simplify these block diagrams.